Good morning everyone. I am Renu Sharma, Assistant Professor, Ajay Kumar Garg Engineering College. Today I am going to start with the next lecture, or we can say the next part 2 of error detection and correction, which we have learnt about the basics of this. We have learnt in the first part. This is the content of my lecture. Contents are introduction, then linear block codes, it is also known as LBC in short form, then generator polynomial, and then cyclic redundancy check, or we can say it is CRC. In the short form it is known as CRC, that is known as the cyclic redundancy check. Now, this is the introduction of error correction and detection. The purpose of error control coding is to enable the receiver to detect or even correct the errors by introducing some redundancies into the data which has to be transmitted. So, what it says, whenever we are transmitting any sort of data, whether it is in the form of 1 and 0 or analog, in the original data you have to add the redundancy bits, redundant bits you are adding, and at the receiver side these bits will be checked that whether the error has occurred or not. Whenever you see that the error has occurred, then either you have to discard that particular message, the original data, or you have to just check those redundant bits and correct that error. So, there are two options are available. We have seen in the previous lecture that how we have detected the error and we have corrected the error. So, you can correct or you can discard. So, the main purpose is to correct the error, so that the original information that you want to transmit will not be wasted. So, there are basically two types of procedures are there for adding the redundancy bits. First one is the block coding that is available, second one will be the convolution coding. So, two types of codings are available, block coding and the convolution coding. So, this is the linear block code. What is linear block code? This is the k information bits or the original data that you are having to be transmitted, and this is denoted by small k. It is given to this block coder. This is nothing, it is the LBC, that is the linear block coder, and it is been received at the receiver side, that is denoted by encoded bits. Now, this is not encoded bits, this is k plus r. You have added parity bits at the block coding coder, so that it will be checked at the receiver side. So, you can identify that whether the error has occurred or not, and you have to just remove that particular error which has occurred. Now, the rate of coding or the rate of encoder is denoted by R is equals to k by n. What is k? K is the original data bits, and what is n? N is nothing, it is known as the code word encoded bits. So, R will be is equals to k by n. So, you can easily see that this is n digit, this is the representation of linear block codes. This representation will going to justify or will going to give you a brief idea or the picture of what is this LBC is all about. It is total number of bits in an linear block code is n, that is n digit code word. It consists of information bits that is having the length denoted by small k, then this is added with the parity bits which is r, and you can easily say it will be n minus k. This will be added, and this is how this linear block code will be generated. Now, next is the generator polynomial. This is a part of the linear block coding. This generator polynomial can be used to determine the generator matrix G that allows the determination of parity bits for a given data bit of m by multiplying as follows. So, we have to just multiply this m message bits with the generator polynomial, or you can say the generator matrix. How this matrix will be generated? First, you will see that this is the C that is generated over here, code word. C is nothing, it is the code word. So, how many number of code words are possible? It is 2 to the power n number of code words are possible using this linear block coding. How you are going to generate? This is the original message. You can see that this is of 4 bits of message are there, and this is the generator matrix. You can say, or this is the generator polynomial. So, this is the generator matrix or the generator polynomial. This is the message you have to multiply. Simply the matrix multiplication will be applied over here, and then this is will be equivalent to the code word. So, 2 to the power n number of code words will be generated over here. This is the first code word that has been generated. Now, other combinations of m can be used to determine all other possible code words. So, how many combinations are possible? This is a big question, but it is very simple to answer, because if we are considering 4 number of bits, then how many combinations are there? It will be from 4 times 0 to 4 times 1, means from 0 to 15. In total 16 combinations are available. So, you can find out this much number of code words by using 4 number of bits, 4 number of bits in your message signal. So, this is about the generator polynomial. Next is the linear block code. The block length C of the linear block code is given by this, that is C is equals to m multiplied by G. This is not the simple multiplication, it is only the matrix multiplication, where m is the information code word block length, G is the generator matrix. Now, the question arises that how this generator matrix will be generated, it will be find. Now, G will be is equals to I k by P. What is I k? I k is nothing, it is the identity matrix. What is identity matrix? If you are considering 3 cross 3 identity matrix, then it will be like this, means on diagonal it is having elements that is equivalent to 1. This is identity matrix, and the other elements will be equivalent to 0. So, this is a 3 cross 3 identity matrix. 3 number of rows are there, 3 number of columns are there. On the diagonal it is having elements that is equivalent to 1, and the other elements in the matrix that is equivalent to 0. So, this is a 3 cross 3 generator matrix, identity matrix. This will be used over here. Then it is followed by this P matrix. What is P matrix? P matrix is nothing, this is the remainder of the x to the power n minus k plus I minus 1 by g x. G x is nothing, it is the generator polynomial for I is equals to 1, 2 up to k, and I is the unit or identity matrix that I have explained. 3 cross 3 matrix, identity matrix I have explained already. Now, next at the receiving end. So, this matrix or this operation will be done at the transmitter side, it is not used at the receiver side. So, at the receiving end, the parity check matrix can be given as H will be is equals to P transpose by I n minus k. So, this is nothing, this is again the parity matrix, but P transpose means whatever P you have used at the generator matrix at the transmitter side, the transpose of that particular matrix will be used at the receiver side, that is H is equals to P transpose by I n minus k, where P transpose is nothing, it is the transpose of this matrix, that is P matrix. So, P matrix is same at the transmitter and at the receiver side. At the transmitter side, it is used along with the generator matrix or the generator polynomial along with the identity matrix, and at the receiver side, whenever you want to check the error which has occurred at the receiver side, you have to use this H matrix, that is at the receiving end, it is equivalent to P transpose by I n minus k. So, this is how this matrix will be generated at the transmitter side and at the receiver side. So, at the transmitter side you have to use the G matrix, which is I k P. At the receiver side you have to use this H matrix, that is P transpose I k. Fine. So, same dimension you can say used at the transmitter side, at the receiver side, this is used at the transmitter side, this is used at the receiver side. Now, next is the parity check matrix. This parity check matrix, how it will be generated? The transpose of this matrix is written over here, or you can see that this will be equivalent to P transpose by I. So, this is H transpose matrix, H matrix, this is H matrix and this is H transpose matrix, that is P I and minus k. The received code vector x is equals to C E. Here E is an error vector, the matrix H has the property. Now, these are the properties of the H matrix, that is the parity check matrix, that is C H transpose will be equivalent to M C P or P I n minus k, which is equivalent to P M P, and this is the XOR operation that is being used over here. This is the XOR operation, this is C P and this is C P. When you are going to XOR this C P with C P, the same value will be equivalent to 0, because what is the truth table of XOR gate? XOR gate truth table will be 0 0 0 1 1 0 1 1. Truth table of this XOR gate will be, whenever the 2 bits are different, the output will be high. Whenever the 2 bits are same, the output will be low. So, this is the XOR operation that has been used over here. This is XOR operation. So, this is received code word, that is equivalent to x, which is equals to C E, where E is an error vector. The matrix H transpose has the property which is being shown over here, which says it is 0. 0 means there is no error has occurred, and if the error has occurred, then it can be corrected using this parity check matrix. So, this is how the parity check matrix will work. Now, next we will move to cyclic codes. Cyclic codes is nothing, it is the name itself is suggest whenever you are going to shift the bits using the shift register. So, whatever code will be generated, it will be another code, that is another cyclic code will be generated. So, it is a block code which uses a shift register to perform the encoding and decoding. The code word with n bits is expressed as, so this is the formula, you can say this is how you have to generate the cyclic code, that is C x will be equals to C 1 x to the power n minus 1 plus C 2 x to the power n minus 2 up to C n. So, this is how you have to generate the particular cyclic code, where each coefficient C I is equals to 1 to n is either it will be a 1 or it will be a 0. So, this is how the cyclic code will be there. Let us say I will take an example of a shift register, only 4 bits I am taking. Let us say this is 1 0 1 1. If I am going to shift that particular number of bits, and the next bit will be equals to 1, then again this will be another code word. So, this is the main property of the cyclic codes, is that whenever you are going to shift the data in the shift register, then the new code is generated, that code is also a part of a code word. So, this is the cyclic code property, it works on the linearity property also. The code word can be expressed by the data polynomial m x and the check polynomial, that is denoted by the C P x, as C x will be equals to m x x to the power n minus k plus C P x. What is C P x? C P x is nothing, it is the remainder from dividing m x x n minus k by the generator polynomial, that is denoted by g x. So, how this generator polynomial will be generated? This will be equivalent to 1 plus x square plus x cube, it can be 1 plus x square. So, this is how this generator polynomial will look like, and you have to divide this m x x and x to the power n minus k by this generator polynomial, that is denoted by g x. So, this is about the cyclic code. Let me summarize once again what is cyclic code. In cyclic code, it works on the linearity property. In case of this cyclic code, it is a kind of block coding is there. It works on the principle of shift register. You have to insert the data in the shift register, means in different blocks are there, like this is an example. This is how this shift register will work. When the next bit will be is equals to either 1 or 0, then this data will be transmitted like this from one space to another space. When this will be transmitted, then means it will be shifted in the shift register, then the new code word will be generated. Now, this is again a new code word, this is not the information which is wasted, this is another code word will be generated. Now, this code word is shown by this equation, that is denoted by C x is equals to C 1 x to the power n minus 1 plus C 2 x to the power n minus 2 up to C n. So, this is the code word that is generated using the cyclic code, where each coefficient, that is C I, is denoted is either it will be a 0 or it will be a 1. So, this is how the coefficient will be generated. The code word can be expressed by the data polynomial, that is denoted by m x, and the check polynomial, that is denoted by C p x, which is given by C x is equals to m x x to the power n minus k plus C p x. So, this is how this check polynomial will be generated over here, where C p x is nothing, it is the remainder from dividing this m x x to the power n minus k by the generator polynomial, that is denoted by g x, and this is an example of the generator polynomial, that is denoted by g x is equals to 1 plus x square plus x cube. It means these terms will be available, or another generator polynomial is also possible, that is 1 plus x square. So, this is how this generator polynomial will looks like. Next, we will see what is cyclic redundancy check, or it is known as, in the short form it is known as CRC. CRC is an error checking code. First thing, it will not going to correct the error, this is a error checking code. The transmitter will append an extra n bits n minus k bit sequence to every frame, called the frame check sequence, FCS in the short form. This FCS hold the redundant information about the frame that helps the receiver to detect the error in the frame. So, this is in the same flow. Let us say k is the original data, you can say it is the data word, you have added r bits to it, that is redundant bits. Now, this is equivalent to n. What is n? N is nothing, it is the final code word that has been generated, and this number of bits will be added in a frame check sequence, that is FCS. So, at the receiver side, if this is an error checking code is there, then this particular frame will be checked, or you can say only the redundant bits will be checked, that whether any error has occurred or not. Then at the transmitter side, this is the transmitter, for a k bit block, transmitter will generates an n minus k bit frame check sequence, that is FCS, resulting frame of n bits is exactly divisible by the predetermined number. So, this is the transmitter side. Now, next is the receiver, it will going to divide the incoming frame by predetermined number. If no remainder is there, then it will assume that no error has occurred. So, what we have seen in the previous slide also, that how this parity check matrix will work, it is denoted by H. If I am going to divide this m x x to the power n minus k by g x, g x is nothing, it is the generator polynomial. If I am going to divide this message multiplied by this value by this thing, and if the division will result in remainder is equals to 0, then we can say at the receiver side that there is no error which has taken place. So, this is the cyclic redundancy check that has been used for error checking. This is not used for error correction. Now, common type of CRC codes that are available, this is the code parity check bits. This is generator polynomial. I have given an example. These are the different generator polynomials are there. Like this is the code parity check bit, that is denoted by CRC 12. Then you can say that the highest power of x in this case will be 12. Next will be CRC 16. The highest power in this generator polynomial will be equivalent to 16. Next is CRC CCI TT. So, this is having the highest power 16 and it is denoted by this generator polynomial. So, what it says, this table basically shows that whatever check bits or code parity check bits you are taking, like CRC 12, CRC 16, CRC CCITT, then it has a fixed generator polynomial. If in the numerical it is given that you have to use this particular type of parity check bit like CRC 16, then you have to consider only this generator polynomial which is having the highest power of x equivalent to 12. Next will be CRC 32, which is having this generator polynomial which is having the highest power of x will be equals to 32. So, this is how this CRC code will work, means these are predetermined, or you can say that a table is provided to you. You can use any kind of CRC codes for error detection, error checking. CRC is nothing, it is the error checking code is there. So, in this lecture we have seen different types of coding in detail, like first we have seen the linear block code. In case of this linear block code, in short I am going to say that this is equivalent to n will be equals to k plus r. These number of bits are added to these original bits to generate this code word. This is in short LBC codes. At the generator or at the transmitter side, you have to generate a generator polynomial or generator matrix will be generated, which is given by G is equals to I k P. P is the parity matrix and I is the identity matrix. At the receiver side, we are having this H matrix, that is equivalent to P transpose and I k. So, this is how this H matrix will be used at the receiver side, that is the parity check matrix denoted by H at the receiver side. Different then we have seen the cyclic codes. In case of the cyclic codes, we have used the concept of shift registers. Whenever the information is incoming, any message bit will be added to this particular shift register, then the data will be transmitted or it will be shifted into the next registers and the data will be forwarded in that particular sequence. Then you can say whatever the data will be generated in the next code, that is again a valid code word. The shifted code word is another new valid code word. So, this is about the shift cyclic codes are there. Then we have seen the cyclic redundancy check, that is CRC. Different types of codes are available for error correction purpose, that is CRC. So, code parity check bits are there. There are different options are available in this table. Whatever CRC you are taking, like CRC 12, CRC 16, CRC CCITT or CRC 32, the corresponding to that these parity generator polynomials you have to consider at the transmitter side, and same is used to be used at the receiver side. So, that the proper type of error detection or correction will take place. So, this is about the CRC coding. So, the generator polynomial g x, whenever and another very important point that you have to consider, that whenever you are going to divide this m x message with x multiplied by x n to the minus k divided by g x, then you are having a polynomial, that is a valid polynomial, and then if the remainder is equals to 0, then you can say then there is no error will take place. So, this is about the CRC coding. So, you have to generate this generator polynomial at the transmitter side, you have to generate this H matrix at the receiver side. This is the generator polynomial, this is the parity check matrix, its value is equivalent to I k p and its value is p transpose I k. So, this is how you have to generate this parity check matrix. This is G matrix and this is H matrix, and these are the differences that you can follow for this topic. So, thank you.